Hello everyone, welcome back. Today we will start the discussion on mobile robots localization and mapping. In the last few classes we talked about sensors and sensing, importance of sensing. Now we will see how we can use these sensors to do the localization of a robot as well as to create maps. So that is the mapping. We need to have the capability of localization and mapping in mobile robots, especially when the robot is autonomous. So as I mentioned in one of the classes, autonomy for robots comes with a lot of challenges. And as I mentioned, the important requirements are the robot need to know where is it and where is it going and how can the robot reach there. So these are the three questions the robot needs to answer. And the first question is, where am I? And that can be answered through localization. The robot can localize itself in a given map or a created map. That means the robot knows where it is. So if there is a large area where the robot is moving and this map is already given to the robot, or the robot has created a map on its own based on the information. Now within this, the robot should be able to know where is it. Suppose this is the robot. Robot should know what is its x and y position with respect to a reference frame. So if there is a reference frame, then with respect to this reference frame, the robot should be able to know what is its x position and what is its y position, and of course its orientation theta also. So that also is important. So if the robot can actually get this information, its x, y and theta somehow through the use of sensors, then we say that the robot is localized itself. So that is basically the localization requirement. Okay, so I already mentioned about, so we need to perceive and analyze the environment and find its position within the environment, and then of course it has to plan and execute. So we'll talk about this part only, the localization part in this discussion. So localization basically requires the perception to be done. So basically the sensors will go and get the data. Sensors will collect the data, and that data will be processed with the information available with the robot. Either the map is given or the map is created, and based on that it do the localization. That is what actually happens in the robots. Now in order to do that, we need to understand a few things. That is basically how do the robot do the localization. Okay, so the first one to the localization method is basically the odometry, or we call it as the dead reckoning. That is, the robot uses its sensors available on the robot and get the position and orientation, and that is basically known as the odometry based localization or a dead reckoning based localization. So the robot needs to know its x, y and theta, and the odometry will provide you the velocity information. So the encoders attached to the robot can actually provide the velocity information, and once you have the velocity information, you can integrate it to get the position information, and based on that you will be, and again using the sensors which can be used for getting the orientation, you can get the orientation also theta. So we saw that we can use compass and other sensors to get the orientation, and odometry can be used to get the position. So that is the simplest way of getting the localization of a robot. But it has got a lot of disadvantages. It cannot be used for a long duration. It can be used for a very short duration because of the errors accumulated will create problem. And therefore we go for the next method called map based localization. Map based localization is a method by which we use the odometry information and the map information and then localize. That is basically the map based localization. And then in map based localization we can go for the probabilistic localization methods, and these two methods are commonly used. One is known as the Markov localization and the Kalman filter localization. So both are basically on map based localization. So you need to have the map information and then map information plus the odometry information plus the sensor information will be combined in order to get the localization of the robots. So, these are the algorithms, Markov and Markov localization algorithm and the Kalman filter algorithms are there, which can be used for map based localization, where we use the we fuse the information from the odometry, from the other sensors, exteroceptive sensors, and then the algorithms will be used to fuse this information and then estimate the position of the robot. So, that is basically the map based localization. And as the robot do the localization, sometimes the map may not be available. So, in that case, the robot needs to create a map of the environment as it do the localization, and this is known as simultaneous localization and mapping, or SLAM. Simultaneous localization and mapping is SLAM. So, the robot will be able to create a map and localize itself within the map simultaneously. Okay, so the map is not given, so the robot does not know the map in advance, but using the sensor information, it will try to create a map, and then using the fusion algorithms, it will try to localize itself within the map. That is basically known as SLAM. And then there is an advanced version of a extended Kalman filter, SLAM, where the SLAM can actually be achieved using extended Kalman filters. So, these are the topics that we will be discussing in this chapter. So, first look at okay. So, before going to the details, let me explain the scenario where the map based localization or the localization is done, where we use the data fusion and algorithms in order to estimate the position of the robots. So, if the robot is moving in the environment, it will be having its own encoders. So, using the encoder data, we can actually use the odometry to get the localization done. That is the primary localization. So, it will predict the position of the robot using odometry, and then it will be having a map given to this, assuming that this map is given. Then it will check with the map, this one, and then see what is the predicted position if the map features are known. So, if it will be having a sensor, and then using the sensor it will observe things, and from the map also it will be getting information. It will check these two information. So, map says that I am supposed to see a wall at 5 meters, but I am seeing a map at 6 meters. I am sorry, I am seeing a wall at 6 meters. So, that means I am actually seeing the same object, but the predicted position and the actual position are not matching. That means there is a mismatch between the predicted position where the robot is currently and where it should have been actually where it is currently actual position of the robot. So, there is a difference between the actual position of the robot and the predicted position of the robot. That is why you are seeing the sensor is seeing at a particular distance, and map says that it should be at a different distance. That means there is a mismatch. So, it will do a matching, and then it will try to recalculate the position, it will update the position, and then that updated information will be stored. So, at every instant as the robot moves, it will keep on doing these activities. Every instant the encoder data will be used to predict the position, and then using that position it will check in the map what are the things that the robot should be able to see, and it will use the sensors to really check whether if the robot is able to see those things, and they are not able to see, or they are seeing at different distances or different locations. That means there is an error between predicted position and the actual position of the robot, and that will be matched using some standard algorithms, or they will be using some fusion algorithms to fuse this information and then get the new estimate of the robot. So, this is the way how the localization works in the autonomous robots. So, every autonomous robots will be having these features in the system, odometry and the external sensors, and then fusing this information and correcting the position of the robot. So, that is what actually the how the localization works based on map based probabilistic approaches. Okay, so we have odometry, then we have localization based on external sensors, and then we use the probabilistic localization methods to recalculate the position of the robot and then estimate the new position of the robot. So, that is basically the process of localization in mobile robots, especially the probabilistic model, where the localization uses the probability of the robot being at a particular location and the probability of the robot seeing an object at a location, and then combining them and getting the new position of the robot. So, this localization principle will be used in almost all the robots which depend on the map information as well as the sensor information for localization. We will see these steps one by one. First, we look at the odometry based localization. How can we localize a robot based on the odometric information? So, that is the first step, where we can use the robot's sensor information and then use that information to estimate the position. Okay, so there are many challenges in localization, as I mentioned, because the robot needs to know its local position. Not an absolute GPS position is not sufficient. The GPS says that you are at this particular latitude and longitude. That is not sufficient for the robot. The robot needs to know within a room or within a given environment where it is. That is the information with reference to a particular frame. Therefore, the GPS information may not be useful in this case. Okay, and then it may require more than one position as a only position as input. It may require many other information for it to plan the activities. So, just in position is not sufficient. Needs to know how far the objects and how to avoid obstacle as it moves forward. There are many things the robot needs to do. So, that itself is a challenge. And then, as I mentioned, the sensor noise, sensor other things are also a problem in localization. We mentioned about this in the previous lectures about sensor aliasing, effector noise, etc., etc. So, all those things will actually lead to a lot of errors in the estimated position of the robots. Okay, sensor noise, as I mentioned earlier, is influenced by the surface illumination, etc., and the measurement principle also it may affect, and because of this it drastically reduces the useful information. So, the useful information that is coming to the user or to the robot will be very much less because of all these reasons. And to do that, we may have to take multiple, to overcome, we may have to take multiple readings or employ temporal and or multi-sensor fusion. So, these things will be required in order to reduce the errors. Sensor aliasing is another one which actually causes problem, because it is known as the non-uniqueness of sensor readings, where the readings, the robot will tell that okay, there is an door in front of the robot, but it can be a door, it can be a cupboard, or it can be a cutout, or it can be anything. So, many to one mapping is possible. So, it can actually map many things to one object. That is basically known as many to one mapping in the environment. Okay, and moreover, the information perceived by the sensor is generally insufficient to identify the robot's position from a single reading. So, a single reading may not be sufficient to estimate the position of the robot. So, these are all challenges in using sensors for localization. And of course, there will be noise from the effector, that is the actuators, the motors will be having their own errors. Though we have many things that the wheel encoders and the heading sensors, when you integrate, it may be easy to do this dead reckoning, but there will be a lot of errors because errors are getting integrated unbound. Because when you use an accelerometer to get the velocity information, and then the velocity information is used to get the position information, we are actually doing an integration. So, any error in the accelerometer is actually integrated, and then the position error will be much more than the actual information that we are interested in. So, these are actually challenges in using sensors. Okay, but unfortunately, we don't have too many solutions for this. We need to live with this kind of issues. and therefore we need to have some methods to reduce the error as the robot moves in an environment. As I mentioned, if you are using only odometry and along with that we are using the dead reckoning with the heading sensors, that may not be really sufficient because it actually keeps on adding errors. So, suppose the robot is moving in an environment, suppose the robot is moving like this, and we assume that the robot is moving straight, both the encoders are giving you the same reading, but the encoder itself is having some kind of an error. So, though we calculate the position based on this, at every instant we try to calculate the position, then we will see that actual position is calculated here, but the robot may be going like this. Calculation will clearly show that your position is here because your encoder data is coming properly and we are just calculating, but the actual position of the robot may be here, and as the time passes this error increases to very large levels, and then the estimation will not be of any use. So, this is something which we need to reduce, but reducing this one I already mentioned about the error sources. We will be having deterministic sources and deterministic errors and non-deterministic errors. So, these deterministic errors can be eliminated by calibration, but non-deterministic errors need to be modeled by some methods. So, we use the probabilistic model as I mentioned earlier. So, we need to use the probabilistic model and then use that one to model the non-deterministic errors. And there are many other sources of error because your terrain may not be flat, wheels may not be having the same diameter, the measured wheel speed may not be correct. So, all those things will also add to error. So, these are basically, some of them are deterministic which can be compensated, some of them are non-deterministic which cannot be cannot be modeled. So, like floor contact, unequal floor contact, slippage, all those things cannot be really modeled. So, that need to be taken into account in the estimation of the position of the robot. In the localization, we need to be aware of these things and to ensure that we have some methods to compensate for these errors. Okay, so let us look at the error model for differential drive robots. So, we know that suppose the robot is at this position. So, you have a robot and the robot is having two wheels as you can see here. Now, we need to develop a model for localization of these robots, and we need to know how the model, the error in the estimated position will vary because of the error in the encoders, because we will be using encoders to estimate the position of the robot. Assume that the robot is initially at x, y, theta. So, the initial position is given as x, y, theta. So, this is the x position, this is the y position, and this is the orientation theta. Now, as the robot moves, you will see that the new position will be, suppose the robot we are here. So, now the robot is at here at next position. So, we say that this is x plus delta x, and this is this may be y plus delta y. We need to know how do we actually get this delta x, delta y, delta theta, and then how much will be the error in delta x, delta y, delta theta, or the total estimated position, how much will be the error in the estimated position also. Assuming that initially there was no error, it was exactly x, y, theta, and now we calculate delta x, delta y, delta theta from this omega 1 and omega 2. So, we have omega 1, omega 2. So, we know that delta x is a function of omega 1 and omega 2, and delta y is also a function of omega 1, omega 2, and similarly delta theta also. Okay, but there are other parameters like the radius of the wheel and then the distance to the center. So, all those things also affect. So, you might you have learned about the kinematics. In the kinematics, we have a method to estimate the position of the robot. We can find out delta x and delta y using this using omega 1, omega 2. So, if we know the error in omega 1, we need to know omega 1 and omega 2, we need to know how much will be the error in delta x, delta y and delta theta, or the total estimated position. So, that is basically known as the error model for differential robots. So, we will take a example of a differential drive robot in order to make it simple. So, we do not consider the other robot for the time being. We just take the differential robot. We assume that we know some of the things about differential robot, and then we use that one to get the estimation. So, if you have this kinematics known, so we know that delta x is given as delta s cos theta plus delta theta by 2, delta y is given as delta s sin theta plus delta theta by 2, and delta theta is given as delta SR minus delta SL by B, and delta S is delta SR plus delta SL by 2. What is delta SR? They are the absolute value of travel distance. So, we assume that the delta SR is the wheel travel distance for the right wheel, and delta SL is the distance traveled by the left wheel, and that is obtained from the encoders. So, we assume that we use the encoder this encoder to get the wheel speed, because it is a differential drive robot. Theta is controlled by the two wheels. So, when there is a variation in delta SR and delta SL, we will be having a delta theta also. So, you can see that the delta theta is delta SR minus delta SL by B, where B is the distance between the wheels. The wheel distance is given as B. So, delta theta is delta SR minus delta SL by B, and then once we have delta theta, we can get delta x as delta S cos theta plus delta theta by 2, and then delta S sin theta plus delta theta by 2. So, that is the way the kinematics can be used. So, you will be able to get delta x and delta y using this information. Okay. Now, the question is, so the new position of the robot P dash is basically xy theta plus delta x, this is delta x, delta y and delta theta. Okay. So, x plus delta x, delta y and delta theta. Okay. So, the new position P dash can be obtained like this. Now, the question is, if there is an error in delta SR, delta SL, what will be the error in this new position P dash? That is what we are interested in. That is basically the error model for the differential drive robots. To do this, we need to look at the error propagation model. So, the error model for the sensor, we say that the sensor has got an error, and that sensor error can be actually represented as a covariance delta SR, delta SL. So, we assume that the covariance in sensing, the sensor covariance can be given as KR delta SR, KL delta SL. Assume that it is a diagonal matrix, and it is proportional to delta SR and delta SL. So, we assume that this is known. Now, if the sensor information is known, then we want to know how much will be the error in x and y, delta x, delta y and delta theta, or we want to know what is the covariance in position estimate. So, for that we use the error propagation model. So, the covariance in the position estimate, new position estimate, is given by this relationship del f position covariance P and then sensor covariance delta. So, assuming that this initial covariance of the position estimate is known and the sensor covariance is also known, we will be able to find out the error covariance of the position estimate using this, where del f is basically nothing but the Jacobian, and this is the covariance, and this is the Jacobian transpose, and this is the Jacobian of the sensor, and then this is the covariance, and then the transpose. Sorry, this is the Jacobian delta position, and then the sensor relationship Jacobian. So, once we have these Jacobians, then we will be able to get the covariance of the position estimate. And how do we get this? So, the del f is obtained. So, this Jacobian Fp for the position estimate Jacobian, we can get it as del f which can be obtained by taking the partial derivative of f with respect to x, y, and theta, because f is a function, this is x, y, theta. Therefore, we will be able to get this as partial derivative here. 1 0 minus delta s sin theta plus delta theta by 2, 1 delta s cos theta plus delta theta by 2, 0 0 1. Basically, we are taking the partial derivative of this previous function, this function. We are taking this partial derivative of this function and then writing it here as the Jacobian here. So this is basically the FP. So this is F delta del RL, which is the Jacobian of the sensor, because sensor also has got the relationship here. That can be obtained like this. F del RL is equal to taking the partial derivative of the relationship between x and delta. So, we will be getting the Jacobian F delta RL also. And for every step, we can actually calculate this, because the theta, delta theta, this information is available. So, we can find out this Jacobian and then estimate the position. Okay, so I will stop here. We will continue this discussion. I will explain this once again in the next class, and then we will continue the discussion on localization using other methods also. Thank you.